So this talk is a deep dive into DynamoDB. Let me start by saying I realize you have lots of choices on where you could be. There's a whole bunch of talks. Thank you for coming to this one. And if you're watching this online, likewise. Every year when I do this talk, one of the things which I think about is why we do these talks. And the simple answer is it's for you, our customers. The thing which I like the most about what I do is to work with all of you and see the things which you build using DynamoDB and in the past with other databases I've worked on. This year I wanted to change things up a little bit. In years past when I did this presentation, it was block diagrams and architecture and stuff like that. This year I figured we'll change it. We're going to do the same things. We're going to do the deep dive, but we're going to do it from the point of view a customer. And we're going to take two actual situations with real customers, talk about an issue which they reported, and talk about the architecture through that. Wrong button. So a quick word about myself. My name is Amrith. I'm a senior principal engineer. I've been in the DynamoDB team for about 6 years now, about 35 years in this business. The thing which I like the most in all of the roles I've had is working with customers. So if we can, after this talk, if you have questions, please feel free to reach out. Let's dive right into it. So what is DynamoDB? It is a document and key value store, and the objective is that we give you predictable low latency at any scale, right? Think about those two things, predictable low latency and any scale. We typically see DynamoDB used in foundational services. What are foundational services? The things like your login, the ability for you to connect to a system, inventory management, like most of Amazon.com, AWS runs on DynamoDB. Control plane of most services run on DynamoDB. These are applications where latency and availability are paramount. Predictable, low latency, and very high availability. Well over 5 nines is what we achieve. And most requests are done single-digit milliseconds. The important thing is you as a customer don't have to bother about all the things which we do in order to deliver these things. You get data, you put data, and that's about it. It's fully managed for you at any scale. So whether you're doing 10 TPS, or you're doing 10,000 TPS, or we've got hundreds of customers who do 500,000 RPS sustained, you'll get the same latency. We aim to give you the same predictable latency. I've talked about scale several times. This is an Olympic swimming pool. Apparently, this is in Barcelona. It is 50 meters by 25 meters by 2 meters. Now, most people in most parts of the world understand 2,500 cubic meters. But in the US, we don't do things that way. We have to tell you how big things are in terms of football fields or jumbo jets. So for all of us here, this is 17,000 bathtubs, metric bathtubs, ostensibly. So let's assume you take all the water out of the pool and you fill your 17,000 bathtubs. And grains of rice. Everyone knows how big that is. I'm not going to tell you how much that is. For every request DynamoDB serves, place 1 grain of rice in the now empty swimming pool. How many days do you think it's going to take to fill this swimming pool? Anyone? Less than 1 day, okay? Brave person there. Anyone else? In less than the time it takes for us to talk through this slide, you would have filled that swimming pool. That's an idea of the scale at which we operate. Every time you go to Amazon.com, put thing in a cart, search, or use any of the many applications which use DynamoDB, 1 grain of sand, 1 grain of rice, 61 seconds, you got a full swimming pool. So keep that in mind when we talk about scale. And if you have any concern whether your application will be, whether we'll be able to serve your application scale, remember 17,000 bathtubs, 1 minute. All right. So we'll talk about the first of these two case studies. Like, I am firmly of the opinion that life is too short to not be having fun. So I hope you have some fun and learn something along the way as well. This is an actual customer incident. I'm not going to name the customer, but it is something which literally happened. The first time this problem happened, we were as puzzled as you probably are going to be when you see this, but it's an interesting way of understanding the architecture of DynamoDB. So this customer came to us and said their application was receiving unexpected write throttling. Now, I should probably pause and say, how many of you here have not used DynamoDB? Okay, so most of you have, so good. So this customer complained about unexpected write throttling. This was a national crisis if this application didn't work. This application had not yet gone into production, but it would literally have been a national crisis. They were conducting a nationwide poll, and they needed this application to work. There had been an older system. It used a legacy RDBMS, and that system was fully rewritten now to use DynamoDB. The old system needed only to do 600 TPS. We'll get into why in a second. But COVID came along, and this old system, which involved people going to a counter and so on, could no longer happen. So they said, we're going to have a self-service mobile application, and the mobile application has to serve 45,000 TPS. So it was going from about 600 up to 45,000, which meant they had to do a full rewrite. So the customer said they were getting write throttling. So the first question we asked them was, what throughput are you getting write throttled at? 800 TPS. No. 17,000 bathtubs in a minute, 800 TPS, there's something wrong with this picture. So we dug into it, we asked them, what's your application? It's a very straightforward application, and to understand this application, I'm going to describe the application almost exactly the way in which it is. The most important thing to understand is anonymity was really important in this application, so keep that in mind. So the workflow itself is very straightforward. They're going to read a table, and they're going to write 3 tables. That's it. All right, what are these tables? First one, a national ID table, the one on the left. This is not real data. This is just synthetic data. I said anonymity was very important. There's a table which has random IDs. And the survey itself consists of 2 tables, a survey table and the personally identifiable information. Now, they're very careful about keeping the data separate, so they came up with these 2 randomized IDs. One's called a PID and one's called a SID. And the basic idea is that the PID ties to the PII table, and the SID ties to the survey table. Now, if somebody has access to one of these, let's see if this works. Yeah. If you have access to the survey data, you can't directly get to the personally identifiable information because you would need this randomized ID lookup. And they made sure that not many people have access to that. So if you need to, you can look at PII, you can look at survey, but you can't ever put the 2 together. But they went one step further, and they did not tie it to the national ID. What they did was, they did a hash of this combination and made a low cardinality hash, which means that if you did go from the random ID to the national ID, you would get some number of people. But you could never go in this direction. You could never say, what was Jack's choice in the survey? So this was the whole premise of the application. So a random ID, personally identifiable information, and the survey information, and they're throttling at 800 TPS. So what did the application actually, how does the whole flow work? They mail something out to everybody, to all registered voters and so on. And in the old system, people would go into a physical location and prove who they were with driver's license or whatever, answer a bunch of questions, and they'd be done. But because of COVID, they didn't have the ability for people to go into a place, so they did this application, the mobile app. So what does the app itself do? It generates the random ID, records the personally identifiable information in the survey, and it puts that one-way hash in the national ID table. Straightforward. 1 read, 3 writes. That's it. Everybody good so far? Okay. So some information here, they got a random ID, and that's going to map to some particular record here. Very straightforward. How can this application, so simple, possibly have right throttling? Like, we were not able to see any way this could happen. So this is a sophisticated customer. They did all the right things. They've scaled their tables, high cardinality keys, and all of that good stuff. So we went one step further. We asked them, tell us about your schema and so on. Okay, so we get a little bit more detail. The national ID table and the random ID table also have GSIs. GSIs are global secondary indexes. And the basic idea of a GSI is it gives you another access pattern. Now, in this case, if you have a AID, which is this anonymous ID, get me the national ID. You'd use the GSI for that. Or if I have a SID and I want to get the PID, I would use this GSI. On the other hand, the primary key on the table will allow you to go from the PID to the SID, as an example. So, simple application. 1 read, 3 writes. This can't possibly be happening. So, next thing we ask them, how big are your items? So maybe they're writing 1 megabyte items, and that's the reason they had a problem. Nope, small items. 500 bytes, 2 kilobytes, 400 bytes. Next question. Is the ID really random? Because that's the only thing we could think of. So like small items, properly scaled up tables. They didn't have LSIs or any other things. Why would they possibly throttle? So we said, is this ID random? And tell me more about your random number generator for this random ID. And they said, oh, it's not a random number generator. For various statutory reasons, this table is populated in advance with random IDs. So they populated this table in advance. And then at runtime, all they did was they would scan this table. So this is the mechanism to come up with random IDs. This is their random number generator. This table is populated in advance. They verified that it's high cardinality and truly random and all that. There's some microservice which is going to generate the random IDs, and what it does, it goes and reads a whole bunch of rows at once. Maybe it reads a batch of 1,000 rows, and it records the last evaluated key. And then when you want an ID, it'll give you one. That's basically how this application works. And they verified high cardinality. And oh, by the way, GSIs are non-unique. We don't enforce uniqueness. So they verified that the SID is also unique. That is their statutory requirement. Something is funky with this random number generator, but it looked right to us. So we said, OK, fine. But we still had some nagging suspicions about it. So then the next question is, where is this right throttling? So obviously, we thought, right throttling must be on the table with the 2 kilobytes. Nope, it's on the smaller write, the 500 byte write. And so here's what we know so far. And they're throttling at 800 TPS. 60 days out, they need to get to 45,000 TPS. So anybody out there have an idea what's going wrong? Just raise your hands if you think you know what's wrong. They're throttling on the PII table at about 800 TPS. OK, I don't see any hands up yet. Good. We were in exactly the same boat. Oh, good. No, I just want to know whether you're with me so far. If you have an idea, great. We'll see if you're right. All right. So let's talk. So we were puzzled. We did not understand why this was happening. So here's how we scale. We scale horizontally. We partition your table You give us a partition key, we partition it. It's basically hash-based partitioning. When you create a table, we ask you for the name of the table, what the primary key for the table is, and your credit card number, pretty much. That's all. And same thing with the GSI. How are you going to pay for it? But notice here, this is not unique. That's the only difference between a GSI and a table. So here's the national ID table. When they wanted to populate this data, what would we do? We would compute a hash. Now, throughout this presentation, I show you hashes. These are not actual DynamoDB hashes. This is just an MD5, actually. So we compute a hash, and then we sort that data based on the hash value. And having sorted it on the hash value, we create demarcations, and we call those partitions. That's pretty much how DynamoDB works. Horizontal scale, hash-based partitioning, fairly straightforward. OK. So a partition is a contiguous range of hashes. All right? So we compute the hash of the partition key, sort based on the hash, contiguous ranges become a partition, and store those on storage nodes. That's pretty much how we work. So the hash which we use, a couple of the properties of the hash, of course, it has to be a fast hash. We do this, 17,000 bathtubs in a minute. So we have to do this hash fairly often. And the hash has to be even, in the sense you can't have a hash which is going to produce the same value at a higher, or some values at a higher frequency than others. Two other properties of our hash. Hash has to be deterministic, of course. And there's this property called avalanche. So let's talk about these two. The deterministic hash basically says, irrespective of which table, who the user is, hash of x equals hash of y, if x equals y. Now, it doesn't have to be for every table. It doesn't have to be for every user. That's just the way in which we implemented it, it turns out. Keep that in mind. The other property I mentioned is avalanche, which basically says that if you have some value, that, if you make a small change to the value, you should have a large and unpredictable change in the hash. So notice, I make a very small change to the value, you get this very large change to the hash. So those are the characteristics of the hash function we use. And it's worked great. Over a decade, we've never had a problem with this hash function. So here's a look at how the random ID table actually would look. There's a PID and a SID. We compute the hash values. We sort the data based on the hash value, and we store it in partitions. That's pretty much what DynamoDB does day in and day out. And when the customer has a request, they do a scan, and a scan walks the table in the order of the hashes. Okay? So then we return last evaluated key, which is the actual attributes in the table. So the next time you come back and you make another request and you specify the start point, we'll continue the scan from the same place. That's basically how a scan works. Anybody have ideas now about what may be going wrong? So here's how the random number generator appears to work. They're scanning down the table. What they appear to see is this data. Let's look at that data. This is what the random number generator is returning. Looks perfectly random to me. What isn't apparent is that it's actually not very random because it is in the order of the hash. Okay? So now they go and write the survey table. This is not the table which was throttling. So as they're reading data from the random ID table and they're writing to the SID, it's going to go all over the place, which is really good because this is the right pattern which they're going to see. This is how you get horizontal scale. You've partitioned your table into, in this case, I think I have eight partitions, and I continuously write, but the traffic is distributed across multiple partitions. Let's look at the other one. I'm reading on the value of PID. Implicitly, I'm getting it in the hash order. Therefore, the data is being written into the PII table, which is also on the same key. Therefore, the write is not randomly distributing across the entire table. And for the first block of some number of random IDs, you go hammer one partition. Then you switch to the next partition, you hammer that partition. So you're not getting the benefit of horizontal scale. And the reason for this, of course, is this is the unintended consequence of our deterministic hash. No matter which table, no matter who the user, no matter which region, the hash value is the same. Now, let me also say we intend to fix this, so don't take a dependency on that, because you will probably be hurt later. When you're scanning a table, when you perform a query operation and you're getting multiple items back in an item collection, remember that the data may appear random to you, but it's coming back to you in sorted hash order. So now how do we fix this? So of course, the first thing which we told the customer is get yourself a real random number generator. And their answer was, yeah, no, can't do that. Statutory requirement, random numbers have to be populated up front. Okay. So 60 days out before this thing has to work, they were also not willing to make huge changes to the application. So one of my colleagues came up with this clever idea where he said, what we really need to do is that you're going to continue to read down this table. This is your random number generator. We're not going to change that. But we want to distribute the write traffic on the PII table. We don't want it to go hammer one partition, then hammer the next partition, and so on. So what we came up with was we just said, when you're writing to the other table, how about you prefix the ID with some 2 characters? Like we said, use TX in front of it. So the reason for this, you make a small change, it changes the hash value a lot. So now, as you read down the table, the traffic is getting distributed all over on the PII table. So now we're back to distributing the load across multiple partitions, and we're in a good place. So this team was asked to benchmark the system for 45,000 TPS. I think they happily benchmarked it at 90,000, and the survey went off without a hitch. So thing to remember is the way we scale is through hash partitioning. If your traffic has items which are, like on a GSI as an example, if you have a large number of items in a table with the same value for the GSI, you're going to get poor performance on that GSI. High cardinality and uniqueness are really important. And if you're ever in a situation where you're reading one table and writing to another table which shares the same key, remember, you could be susceptible to this problem till we fix it. So it's going to take a while for us to fix this, but we do hope to fix it pretty soon. So benchmark was a success. The survey was conducted, and life was good. So that was the first one. And when this happened, we literally had never realized this problem. But now that we know this problem, this is the way Murphy works. Once you know there's a problem, you run into it every now and again. Every couple of weeks, we hear of some customer who says, oh my God, hair on fire, crisis, my application is throttling. Turns out to be the same problem. So if you are building an application, keep this in mind. It's a pattern which can give you sleepless nights. So to you, the key takeaways are, we have consistent hashing. This could create a problem for you. This is the way DynamoDB works today. Hopefully we'll fix it soon. And probably, yeah, I'd say certainly a couple of times a week we hear, or a couple of weeks we hear this. And it is easy for you to fix if you're able to use the power of the avalanche and make a small change. So if you're reading one table, as you write to the other table, don't choose the same key value, and you won't have this problem. So debugging throttling used to be very hard. When we ran into this problem for the first time, it was about 4 and change years ago. CloudWatch Contributor Insights is literally the only way to do it, but it used to be very expensive. And when we told customers to enable CloudWatch Contributor Insights, they would say, it's too expensive, can't do that. And they can't enable it once the problem happens. You need to have it when the problem's happening. So we introduced throttle keys only, which means we only log when there's throttling. You pay substantially less. The other thing which we did was when you do get throttling, we return enhanced error codes. These are backward compatible. You don't have to make any change to your application. The exception just identifies the exact resource and why. So in the case of write throttling, you sometimes will get throttled if your GSI is generating back pressure. It will identify which GSI for you as well. So if you do face throttling, keep that in mind. There's 10 new metrics which we now have in CloudWatch Contributor Insights with this. One thing which I will mention very briefly, I said partition key and sort key. In the past, like up until a week ago or so, a partition key and a sort key were a single attribute, which meant that if you had a complex schema, it became a little bit hard for you to model that. So we had customers who needed to do these funny things, like this hack where you put a customer ID and an order ID and so on, and then use begins with and contains and so on the sort key. All very hacky. And also, if you want to have the customer ID in the key and you want to store it as an attribute unto itself, there's a problem. You're paying twice for the storage, and the two of them can get out of sync. The problem with redundancy is always you could have conflict between it. There's correctness issues. If you didn't, and you did not want to pay the price and have redundancy, it became hard for you to evolve your schema over time. Because if you need to build another GSI, as an example, and you wanted to use order ID, now you have to go backfill it, pull it out from the middle of this key. Became a pain. So as of, I think this was a week ago, we launched this. You can now have up to 4 attributes in your partition key and your sort key. Makes for substantially easier data modeling. Right now, this is supported for GSIs only, and in the future, we'll see whether we do this for tables. The links there are to our documentation. Of course, if you want to see Alex's LinkedIn post, you can see that as well. We also now have MCP support for schema modeling. So if you are so inclined, we have a very good schema modeling advisor, which will take the benefit of these new capabilities. So with that, let's move on to the next one. And again, this is a similar, this too is a customer reported problem. So here is a view of a tool we use internally. It's called Hawkeye internally. If you call support, one of the things which they ask you is for your subscriber ID. And with your subscriber ID, we can look at some of this kind of performance metrics about your application. So here's data for 7 days for an actual, for a real customer. That's 7 days worth of data. That's the traffic history, and this shows reads and writes. Reads on the left, writes on the right. And the peak to trough is about 2000x. Now, this particular application, once a day, runs some job which drives some batch job which runs a fairly high rate relative to the rest of the day. So this customer application, this is how the application is supposed to work. This is not an anomaly. This is literally what they want. And their issue was this is the continuous interactive workload, which is the low traffic period. And then these are the spikes, which is the batch part of their workload. Now, this is the peculiar thing about this application. When the traffic is low here, their latency is high and variable. And when the traffic is high, the latency is low, very acceptable, but also just a flat line, predictable low latency. Now, this is completely counterintuitive. Normally, you would assume that high traffic, you have high latency. Nope. High traffic, very good latency. Low traffic, horrible latency. Have any chance one of you has run into this? Ever seen this before? No, I know there's one customer who has. They're here, but this is literally data for their application. Now, you can't see what it says there. Oh, this is the average. And in case you're interested, we do store other metrics as well. We store P90, we store P99. This is the P90, 90th percentile, same exact pattern. So one of the things which we did was to try and understand this, built a simulator so that we could simulate this in the lab. And we were able to do that. High traffic, low acceptable latency, low traffic, horrible latency. Peculiar situation. So to understand what this is doing, what this application is doing, by the way, those are the request types. That's get item and put item, which are in use here. Next day, same behavior. Okay? Anybody have ideas on what's probably going wrong? Just show of hands if you understand what it is. Yes? Anybody? Good? All right. So we asked them, what's your application look like? And this is more of a description of the simulator we built, but they have the continuous traffic. They have the batch. The batch is the one which drives the high traffic. And they've got this fleet of instances. In our simulation, we had 150 hosts, which we were driving traffic through. And that's DynamoDB behind. Very straightforward. What could possibly be going wrong? How can you have a situation where you have high traffic and you have good latency, and you have low traffic and you got horrible latency? So to understand why this happens, let's dig into the architecture of DynamoDB. This is the application. It connects to us through an SDK. You resolve the public endpoint. You get pointed to a load balancer. Behind the load balancer, and by the way, load balancers are in multiple AZs. Behind the load balancer, we have request routers. Every request which you make needs to be individually authenticated and authorized. Are you who you claim to be? Is your SIG-before signature correct? Are you permitted to do what it is you're trying to do? Every single request, we have to do that. To do that, we look up some metadata. We rate limit you if you're going over whatever your provision limit is, or if your table is not able to scale. Your data is actually stored on storage nodes, and the request router's job is to figure out which storage node it should send the request to. And down on the storage nodes, all data is encrypted at rest, so we need to go to KMS to get the decryption keys. And again, there's rate limiting on the storage nodes as well. So these are the throttling limits which we talked about in the previous one. Now we have to do this stuff. What did we say? 17,000 bathtubs a minute, right? So we use extensive caching in all of these things. So the request router is going to maintain caches. It's going to cache metadata. It's going to cache your identity information. Your TCP connection from your application goes from your application to a request router. So as long as you use the same connection over and over again, you get the benefit of this cache. If you go one request here, one request there, you may not get the cache benefits. So we do this hundreds of millions of times a second, and it is physically not a good thing for you if you're going to be reconnecting on every request, because you have to go through the entire TCP socket setup. You have to go through TLS. Okay. Why am I telling you all of this? And of course, there's authentication, there's caching for authentication, which you have to keep in mind, and all of the metadata which we're going to use. Data is on the storage nodes. We've got encryption keys to deal with. And in your application, you have connection pools. So going back to where we were, if you manage to get to the same request router over and over again, you get the benefit of these caches. If not, you don't. So wherever possible, try and use long-lived connections. In the case of this particular application, the issue they were having was they were not getting the benefit of the cache. So if their large traffic used this large fleet of hosts, when they were doing their continuous traffic, when the batch was not running, that was almost 2,000 times less traffic. So our hypothesis was that they're not getting the benefit of the cache because of the number of hosts which were involved on their side. So we asked them how many hosts they had. For the purpose of my simulation, I had 150, so I'll just stick with that. I think the customer said they had a few thousand containers. Don't quote me on this. And the bulk was 20,000 TPS, and continuous was 10. This was the numbers which I said, 2,000x. The tables, these thousands of hosts or thousands of containers, they're provisioned this way because they're statically stable. And statically stable basically says that you want to be able to continue to serve whatever traffic without needing to make a control plane change. God forbid, you're not able to scale up in time, you're not going to be able to serve the traffic, so they're scaled to peak all the time. So that's the requirement, and maybe they want to accept bulk ingestion at any time. Maybe it's not once a day. So one option is reduce the host during the interactive time. That is not something which they were willing to do, and also they're in a regulated industry. It'll take a while for them to actually try it out. So our simulation was this: high traffic, low latency, low traffic, high and variable latency. We were able to recreate this in the lab perfectly. And so if you want to take a picture. So what we did was to reconfigure it so that the continuous interactive traffic only went to a small number of hosts. That's the point where we reconfigured it flatline. Because now they're getting the benefit of all the caches they need. So we talked about, so that's the configuration which gives them the good performance. Now, these are two of the things which they could do if they wanted to save money. Run that at low traffic and scale up when they have higher traffic, but this is not statically stable. So while auto-scaling would save them money, it does leave them with an application which is bimodal. So I believe that the configuration they have is the right one to run always with the same number of hosts. But the recommendation we made to them was that they should send the low traffic to a small number of hosts and not to all the hosts. In our simulation, certainly, we showed that that would be beneficial. So I'm going to wrap up by saying I've built applications with databases for several years, and it is always important to understand how the database actually works. Not knowing how the database works means your ability to build an application is substantially less. Understanding what goes on inside is really important. And equally, anybody can go to a hardware store, anybody can buy paint. But it takes a certain amount of thought and some human creativity to come up with art. What our customers build, what you're building, are some really hard, complicated applications, which take a fair amount of thought. So we're here to help you and help you build these applications, and please keep the feedback coming. Thanks a lot.